All right. Hello, everyone. Let me just get set up here real quick and we can begin. Just 1 second. Okay, glad to see you all here. Let me welcome you to this presentation prepared by Globe Tech School. I'm your presenter for today. Some of you may probably have visited our webinars before and remember my presentations in English. And as you know, previous presentations mostly dealt in transformer maintenance and power distribution and maintenance of transformer oil, etc. But Globecore also does other things. And today we're going to talk about one such thing, about, as the title implies, the production of modified bitumens. So without much further ado, anyway, let me just remind again that if you need a certificate of attendance of this presentation, you can request one from Globecore. You'll receive that. Also, I'm sure there will be questions during the presentation. So please ask them in the text chat. We're not going to stop the presentation to answer them in real time by voice, but I have my colleagues there to answer those questions for you. If the time runs out before we can answer all questions, which happens sometimes, no question will be left unanswered. Somebody will get back to you if your question wasn't answered during the presentation, during the webinar. So with this out of the way, I guess we can start talking about bitumen. Right, so first of all, let's go back and talk history a little bit. The history of using the bitumen goes back about 5,000 years. In between the rivers Tigris and Euphrates, the cradle of civilization, I guess as we know it, in Persia and in India, bitumen was used even then as a protective and binding material. The ancient Romans also used bitumen for construction work and for water protection. However, during the construction of roads, bitumen wasn't really used for a very long time until pretty much modern times. Even the Romans, who are famous for their road network that they built in Europe, they made significant progress in road construction, but they did not use bitumen to its full extent anyway. Next slide, please. So the further development of bitumen technologies only began in the Common Era, so much later. In 1712, Juan de Reni discovered a bitumen deposit in Switzerland and experimented with mixing small pieces of natural bitumen with rocks. And a few years later, he presented his thesis based on his research entitled Natural Asphalt Binder. And during this time and over the next 150 years, the bitumen that was used for construction of roads was a natural bitumen from the island of Trinidad. However, the invention and development of the oil distillation process quickly ended the era of using natural bitumen. At first, a mixture of natural bitumen with oil distillation products were used, and later on, preference was given to distilled bitumen. This was facilitated by the research of de Smet, who in 1881 patented the technology of blowing hot air through bitumen, and so he produced so-called oxidized bitumen. Next slide, please. For some time, advances in science and technology kept up with the requirements of the road industry. However, traffic intensity constantly increased, the traffic loads on road surfaces increased, and that caused premature deterioration and destruction of roads. So despite the fact that the technology of oil distillation was constantly improving, the quality of bitumen as a distillation product only got worse because of a more deep refining of oil in order to increase the output of fuels and other light fractions. That led to deterioration in the quality of that bitumen. In practice, straight and modified bitumen has a few drawbacks and limitations. It has high thermal sensitivity, which means that it softens at higher temperatures and becomes brittle at low temperatures, and the range is rather narrow. It has poor mechanical properties and low elasticity, and it tends to age a lot. So there are the limitations that we want to overcome, ideally, if we use that in roads. Next slide, please. So if we want to improve the quality of bitumen that we use in our roads, the only way to do that is with additives, right? So one of the first additives used in practice was rubber. First, it was natural rubber and then synthetic rubbers. For the first time, the introduction of rubber into bitumen is mentioned in British patents. The first patent for such a mixture belongs to Hancock. In America, a similar patent belonged to Charles Nelson Goodyear. And in 1844, a Castle patent appeared for the use of such bitumen mixtures in road surfaces. The first experimental sections of asphalt concrete pavements using modified bitumen were built in a number of Western European countries in the 1930s. And many areas of asphalt pavements using modified bitumen have proven themselves very well in heavy traffic conditions. And so the advantages of modified bitumen became quite apparent. Next slide, please. So modified bitumen has a lot going for it. There is quite a bit of advantages, and they're all very important. So let's briefly run down that list. First of all, it exhibits very good contact with the mineral materials. It has a pretty good low temperature flexibility and elasticity, so it doesn't become as brittle as fast. And also it doesn't tend to flow that much at high temperature, so that temperature range is wider. It quickly relieves the tensions and stresses that appear in the layers of the road surface due to the traffic loads. It's quite resistant to fatigue loads occurring with cyclic temperature changes. And it's frost resistant and has an extended temperature range of operation, as I mentioned again. And it's just more strong mechanically, physically stronger. So the issue of making bitumen with the required properties is relevant even today, because the grades of road bitumen that are made from oil, they don't really meet the requirements of road construction industry in terms of low temperature cracking resistance, heat resistance, elasticity, adhesion properties, especially with respect to the surface of mineral materials from acidic rocks, and also this goes for aging resistance. That is also improved. Even modern technology for the production of bitumen doesn't present such possibilities, because the improvement of one parameter of bitumen quality will inevitably worsen some other parameter. For example, if we increase the softening point, then we get a deterioration in fracture resistance, right? And an expansion of the plasticity range reduces the resistance to aging, for example. Next slide, please. So as I mentioned, the main purpose of introducing those modified additives into bitumen is to reduce the temperature sensitivity of the binder. So to increase its hardness in summer and decrease that in winter. And we also want to make it more elastic. So we want to give it an ability for reversible deformations in the entire range of operating temperatures. If this goal is achieved, then asphalt concrete with the use of modified additives has increased shear resistance, better low temperature crack resistance, and better fatigue durability. Today, polymers are most often used as modified additives for road bitumen. So practically every known polymer out there has been tested in bitumen polymer compositions, while the range of the polymers that are actually used in practice is rather narrow. A necessary condition for obtaining a polymer bitumen binder is the compatibility of both components, meaning the ability of a polymer to dissolve or swell in a bitumen dispersion medium. Among polymers, what we use are elastomers, thermoplastics, and thermoplastic elastomers. Those are the most commonly used polymer groups in road construction. Elastomers are polymers with highly elastic properties in the temperature range of operation. Those are synthetic rubbers in various physical forms. They can come as powder, granules, or even liquid. This group includes ethylene, propylene, butadiene, etc. Rubbers modify both bitumen and asphalt concrete mixture. There are thermoplastics, which include polyethylene, atactic polypropylene, for instance, the ethylene copolymers. Among them, you can have ethylene vinyl acetate, EVA. We have a copolymer of ethylene and acrylic acid, also known as alveoli. And then we have thermoplastic elastomers, and those are polymeric materials capable of reversibly passing when heated into a highly elastic or viscous flow state. And these are styrene block copolymers. You can name styrene butadiene styrene, SBS, very well-known thing. Styrene ethylene butylene styrene, SEBS. And there is styrene isoprene styrene, also known as SIS. So modification of bitumen with elastomers causes an increase in the softening temperature, a decrease in cold flow, a decrease in the dependence of penetration on temperature, a decrease in the brittle point, and the ability to withstand multiple elastic deformations, and also an increase in extensibility. Rubbers are introduced into bitumen material in the form of crumbs, granules, solutions in liquid hydrocarbons. There are powders, there is latex, and there are also dispersions in non-aqueous mediums. The introduction of thermoplastics increases strength, cohesion, fatigue resistance. It prevents cracking. At the same time, it imparts elasticity and reduces susceptibility of the material to temperature fluctuations. Thermoplastic elastomers are a class of synthetic polymers consisting of hard and elastic segments. The combination of these segments provides thermoplastic elastomers with both high strength and elasticity. Flexible and resistant bitumen coatings are produced by adding SBS rubber to styrene butadiene rubber to bitumen. The most widely used polymers of the SBS type are due to their ability not only to increase the strength of bitumen, which is achieved also by other types of modifiers, but also to give the polymer bitumen composition elasticity, which is a property inherent to polymers, and it manifests itself at a low concentration. So we're talking like 3 to 5% by weight of bitumen. The use of bitumen modified with an SBS polymer in the asphalt mix provides the road surface with the ability to quickly relieve stresses that arise in the surface layer due to traffic loads on top of the layer. Next slide, please. So a few words about the structure and properties of polymers, polymer modified bitumens. According to the modern concept, bitumen is a complex colloidal dispersed system in which the discontinuous phase, asphaltenes, is surrounded by a layer of polar resins that form micelles. And these micelles are immersed in a continuous maltenic phase, which is a mixture of aromatic and saturated hydrocarbons. Therefore, it's believed that polymer-modified bitumens are a colloid and a colloid, so to speak. Next slide, please. So in bitumen polymer mixtures, both dispersed phases, that is, asphalt resinous substances and added high molecular polymers, compete with each other for the dispersion medium. Styrene and butadiene are compatible with aromatic and non-aromatic components of bitumen, respectively. And it is this property that explains the strong interaction between SBS and bitumen. Butadiene blocks mixing with bitumen swell and absorb a significant part of the maltenic fraction. And polystyrene blocks, less compatible with bitumen, are broken into isolated domains, thereby providing positions for later links. And depending on the ratio and chemical structure of the components of the dispersed phase and the dispersion medium, a certain spatial structure of asphaltenes and a swollen polymer network is formed, lattice, is formed above a certain critical concentration of the polymer, the critical concentration of structure formation. This structure can be a special lattice of polymer within the coagulation framework of asphaltenes, or a spatial network of asphaltenes and polymer. And these polymer structures impart their mechanical and rheological properties to the original bitumen. At low polymer concentrations, the compositions can be considered dispersion strengthened. In this case, hardening occurs because fine dispersed particles impede the movement of dislocations in the matrix bitumen. The degree of hardening is proportional to the resistance of the particles to the movement of dislocations. And this effect is observed most when the content of the dispersed phase, i.e. polymer, is 2 to 4%. So if you look at the properties of polymer bitumen compositions with 3 to 5% polymer content, you will find a noticeable increase in the brittleness point without increasing the deformability of bitumen. It's obvious that a decrease in the brittle point occurs due to an increase in strength. At a higher concentration of polymer in bitumen, the compositions can be considered fibrous or layered. This matrix then turns into a medium that transfers the physical load to the fibers. And in the event of fibers breaking, it quickly redistributes all these tensions and stresses. Such compositions are characterized by increased strength, elasticity, and resistance to fatigue fracture, which is especially necessary if we want to ensure the operational reliability and strength of the material. And the process of destruction of such composite materials begins with the growth of microcracks. And then, upon encountering a particle of high modulus rubber or polymer, this process slows down, then decreases, and then stops altogether due to the relaxation or of overtension at the crack tip. Next slide, please. Modified bitumen is a very common product that is used in many industries today. And here are some of the uses of modified bitumen. The performance properties of bitumen really make it necessary in many fields. And among such typical applications are road construction, of course, making asphalt concrete of the top pavement layer, surface treatments, making protective layers of cement concrete pavements, or crack stopping membrane type layers, for instance. It is used in preparation of drainage asphalt concrete and for production of bitumen elastomeric sealing sealants. It's also used in hydraulic engineering. It's used for coating of potable water storage facilities, for lining of water supply pipes, for instance. Coatings by modified bitumen provide very reliable protection against water leaks in pools, reservoirs, dams, and similar things. And it's also used in roofing. Modified bitumen is used in the production of roofing felt, roof shingles, I'm sure you're familiar with those, and waterproofing cardboard, which are all waterproofing materials for any industrial, civil, or any other structure that's out there. Next slide, please. Right. Let's touch on the types of dispersed bitumen structures. The composition of PMB, excuse me, includes viscous road bitumen, a polymer, and a plasticizer. Therefore, a change in the quality and quantity of one of the components inevitably entails a change in the quality of PMB. Studies have found that the properties of PMB depend on the properties of its ingredients, while the type of dispersed structure of bitumen have the most significant effect on the properties of PMB. So we distinguish between bitumens types 1, 2, and 3. They can be identified with colloidal systems of gel, sol, and sol gel. For simplicity's sake, we can represent the structure of bitumens as consisting of an asphaltene core surrounded by a shell of adsorption, solvation layers of resins. And these aggregate particles are distributed in the oil environment. Type 1 bitumens have low resistance to oxidizing factors during processing and basically in the production of asphalt concrete. Type 2 bitumen has a few advantages, such as high cohesion and deformation resistance in an elastic viscous state. It has increased resistance against oxidation that cause aging. The disadvantages, however, are lack of elastic and elastic plastic states, low heat resistance, and poor water resistance. So residual bitumen mainly belongs to this type 2. The structure of type 3 bitumen is considered optimal for road construction. And this type of bitumen does not have any obvious disadvantages over of the types 1 and 2. Grades of road bitumen that correspond to the third structural type 3, are recommended for use in all roads and in all climatic zones. And the introduction of a reactive surfactant into bitumen of type 2 can actually transform it into bitumen type 3. Next slide, please. So for the formation of this spatial network that I've mentioned in PMB based on road grade bitumen, the minimum polymer content is about 2 to 2.5%. And if we're doing this based on petroleum bitumen, it's 3.5 to 4%. So an increase in the content of SBS-type polymers above the specified minimum is necessary sometimes if it's required to increase the softening temperature, extensibility, and elasticity at a temperature of 0 degrees centigrade, as well as when we have to work with low viscosity bitumen, petroleum, petrochemical bitumen, and type 1 bitumen. An increase in the content of oil plasticizer is necessary in the following cases. If we want to reduce the brittle point, if we want to increase elasticity and extensibility at 0 degrees centigrade, and uniformity of PMB, it's necessary when working with high viscosity bitumen, for example, 40-60 road bitumen, as well as when we deal with petroleum bitumen and type 1 bitumen. We also do this to increase the workability and compaction of polymer asphalt concrete mixtures. Next slide, please. As always, there are standards for products, and bitumen is no exception. There are several systems for assessing the quality of bitumen that are used in the world. There is the European system reflected in the EN 12591/2009. This is called Bitumen and Bituminous Binders, Specifications for Paving Grade Bitumens. And there is the American system, SHRP Superpave. At the heart of the European system, bitumens are classified according to the penetration index. That is the depth of penetration of a needle into the bitumen at a temperature of 25 C, with only a small difference in the ranges of zone separation. The main indicators included in the European quality certificate for bitumen are as follows. There's a needle penetration depth, soften point, and resistance to aging, which is assessed by residual penetration. It also includes the change in softening temperature and mass after heating to 163 C. The regional norms of the European standard, in addition to the mandatory ones provided by the standard itself, include the requirements for penetration, dynamic viscosity at 60 degrees C, frost brittle point, and kinematic viscosity at 135 degrees centigrade, which is determined using a capillary viscometer. Next slide, please. In the case of low viscosity bitumen, the requirements are simplified and somewhat reduced in volume and extent. The leading parameter of the consistency of low viscosity bitumen is just the same as viscous bitumen, is penetration. So within its limits from 250 by 0.1 millimeter to 900 by 0.1 millimeter, there are 4 grades of bitumen that are classified in this standard, and those are 250 by 330, 330 by 430, 500 by 650, and 650 by 900. And we can go to the next slide. So we've talked about some of the parameters of bitumen. Now let's overview how these parameters are tested. On this slide, you can see the common tests performed on the road bitumens. And these are penetration, softening point, and frost brittle point. And in terms of physical and chemical parameters, bitumen must comply with the requirements and norms specified in the standards to be used in production. Next slide, please. The American Superpave system of standards was developed from 1987 to 1995 because the traditional quality parameters for assessing bitumen that have been in use for many decades came under significant criticism. The main argument of that criticism boiled down to the fact that these indicators don't meet the operating conditions of bitumen and roads, and they're only based on practical experience and empirical dependencies, and not on any fundamental physical or chemical principles and laws. So the Superpave system of specification focuses on the determination of the rheological properties of binding materials, taking into account 3 life stages of bitumen. The first life stage is transportation and storage. The second is changing the properties of bitumen during the production and laying of the asphalt mix. And the third is the change in the properties of the binder during its lifetime as part of the pavement. So the accepted classification of bitumen according to the operational conditions of the road structure of the road surface takes into account all stages of the use of bitumen, from the oil refinery to its use in the production of asphalt mix and its use in the pavement after a certain duration of time. In accordance with this system, the entire territory of the United States is divided into 37 road and climatic zones, which are called performance grades, PG. This division is based on the operating conditions of bitumen at low temperatures, meaning the temperature of the coldest winter day, and the highest summer temperatures, which are calculated as an average temperature of the 7th hottest day of the summer. And based on these air temperatures, the temp of the upper layer of the asphalt concrete pavement corresponding to them at a depth of 2 centimeters is calculated. So the designation of the binder grade, for example, you can see something like PG 8234, means that it should work well at a high temperature of the pavement, up to 82 degrees centigrade, and at low temperatures down to minus 34 centigrade. So this is what those numbers stand for. And in the PG 4634 zone, respectively, at temperatures of plus 46 and minus 34 C. And between these two extremities, according to the operating conditions of bitumen in the layer, there are another 35 zones of classification. The principle of selection and use of binders is that the values of all quality indicators included in the standard at certain specific temperatures should be the same. So in any zone, any binder must provide the same performance properties of asphalt mix. At temperatures from plus 46 to plus 82 centigrade, they must be sufficiently strong. And at temperatures from minus 10 C to minus 46 C, they must have the same resistance to crack formation. The gradation of zones from low to high temperature is made at 6 degrees centigrade steps. So as an example, this slide shows the requirements for bitumen grades PG 4634, PG 4640, and PG 4646. So as indicators for assessing the suitability of a binder for each of the zones, the following are used. True viscosity, shear index before and after aging in a thin layer or under pressure, modulus of stiffness, critical deformation, and coefficient of plasticity. Next slide, please. And true viscosity is a characteristics that allows us to evaluate the ability to pump a material through pipelines and its ability to combine with minerals, the stone material in the road surface. It's measured or determined rather at 135 degrees centigrade using a Brookfield rotational viscometer. The principle here is to measure the resistance, physical resistance of the bitumen layer located in the gap between the rotor and stator that shears at its resistance to shear at a certain rotor speed. So the viscosity is automatically measured from the known torque and known rotational speed. And it's accepted that the viscosity of the binder at a temperature 135 C for all binders should at least be, or ideally better than 3 Pascal seconds. To assess the strength of bitumen at high temperatures corresponding to a particular PG zone, we use the, basically, the complex shear modulus G and the tangent of the angle of mechanical losses are determined using a dynamic shear rheometer, DSR, which performs sinusoidal oscillations in a plane-to-plane pattern with a frequency of 10 radian per second. And to assess the crack resistance of bitumen binders, several indicators are used. The first is the stiffness modulus at temperatures of 10 degrees centigrade below the minimum asphalt concrete temp adopted for each specific zone. This stiffness modulus must be equal to or less than 300 MPa. It's determined using a special device called a beam rheometer, which makes it possible to estimate measure the deflection of a bitumen beam supported on pivotally supported on 2 supports with a load placed in the middle of that span. And this device is called a bending beam rheometer. In the road surface at low temperatures, bituminous binders are subjected to stretching. In this regard, one of the criteria for assessing crack resistance is their deformability at low temperatures. As a result of this test, the temperature is determined at which the specimen tested in tension at a speed of 1 millimeter per minute. When it breaks at a certain deformation, at a certain, and the deformation must be at least 1%. So for such tests, it's very important to have a capacity to measure this deformation very accurately. So mostly we use laser micrometers for that. And the temperature in this test is maintained with also with high accuracy of plus or minus 0.1 degrees centigrade. So in the American system for assessing the quality of bitumen binders, a great attention is paid to the change in the properties over time, both at the production stage and during actual lifetime in the road surface. And this change can be called aging, I guess. So the SuperPave system provides two types of aging tests. The first test is performed by the RTFOT method in a thermostat with a drum that rotates at a speed of 15 RPM, in which 8 cups with a thin layer of bitumen are placed. Each sample is blown with a stream of air. The test temperature is 163 degrees centigrade, and it takes 85 minutes. Samples after such heat aging that simulate the production process are tested in order to determine the loss of mass and modulus of rigidity. And this method is used to simulate aging during the preparation and laying of the asphalt mix. The remaining binder is scrapped off of these cups for a pressure aging test. And the pressure aging test, also known as the PAV, pressure aging vessel, is designed to determine the influence of the environment during the use of asphalt concrete, the influence on its crack resistance at low temperatures in terms of the stiffness modulus, plasticity coefficient, and or its limited deformation. At a pressure of just over 2 MPa in the aging chamber, this pressure is created by compressed air in the chamber. The temperature is set in the range from 90 to 110 degrees with an accuracy of plus or minus 0.5 degrees centigrade. And cuvettes containing 50 grams of this material each are kept in the chamber for 20 hours. The cuvettes removed from the chamber are also kept at a temperature of 163 degrees for 30 minutes in order to remove any air that may have been absorbed by the bitumen. And after this process, bitumen is tested in dynamic shear rheometers, in the bending beam rheometers, and the dynamic tension tests. So the SuperPave system that we've discussed does have both advantages and disadvantages. And the advantages are the application of fundamental physical and mechanical characteristics of the binder. It's the uniformity of requirements for the various types of binder. It's the relationship between the requirements and the actual operating conditions of the road layers. It also takes into consideration the aging process of the binding material and the process of its preparation and operation as part of asphalt mix pavement. And the system uses computer technology and in the research and processing of results, which increases the overall reliability and precision. However, there are limitations in the system, and these include expensive and complex equipment necessary. The cost of a laboratory setup can go north of $350,000 to $500,000 or so. There is also the need for highly qualified personnel, obviously, to operate that equipment. The tests take quite a bit, so the duration of these tests is a limitation of sorts. This system also does not take into account the effect of the mineral substrates on the properties of bitumen, and it excludes the possibility of assessing the adhesive and cohesive properties of binding materials. It should be noted, however, that the existence of the SHRP SuperPave system doesn't mean a complete rejection of the previous bitumen quality indicators. In lab practice in the United States, the penetration depth is used to identify the IC20 grade of bitumen. They also use flash point, solubility in organic solvents, true density, and soft point. These indicators in the USA are part of the so-called SHRP Plus package of requirements. So the features of quality assessment in accordance with European standards are simplicity, relatively lower costs, also repeatability and objectivity of the indications. The main limitations are the use of penetration and softening temperature, which indirectly characterize the performance of the binder in asphalt concrete, and also the limited ability to predict the service life of road surfaces using them. The European standard does not provide for the determination of the amount of evaporated diluent, nor does it provide for a softening point of the residue after heating. However, the European system for the standardization of bituminous binders is quite balanced in terms of the cost of experimental work, and it corresponds really well to the current stage of development of bitumen technologies. So it's also okay to use. And we can go to the next slide. So I've mentioned using rubber for modification of bitumen. This is where we'll start now. So let's consider some methods for modifying bitumen. And from the point of view of environment and disposal of, as you know, there is a problem. There is a lot of vehicle tires out there, so they must be disposed of somehow. And not only tires, there are a lot of rubber products and waste that must be used or somehow recycled. So the use of crumb rubber is of great importance in that regard. And we can use that to make modified bitumen. And this is one of the reasons for this modification method. So there is environmental feasibility of organizing large-scale disposal of used tires and other industrial waste, rubber waste. Some other reasons are the low cost of the modifier, because cost of the rubber crumb is on average about 5 to 10 times less than the cost of rubber and polymer additives such as SBS. We also get a pretty high quality of the modified bitumen. The bitumen modified with rubber crumb is not at all inferior to the quality of bitumen modified with synthetic rubber. So when making bitumen rubber compositions, the technology process involves complete homogenization of this mixture of bitumen with rubber, followed by vulcanization, and that leads to cross-linking of micromolecules. The traditional technology for obtaining a homogeneous RBB, rubber bitumen binder, provides for mechanically mixing or physically mixing of rubber crumb in the amount of from 5 to 30% by weight with bitumen. Tar, such as tar, recycled asphalt, or any mixture thereof. And this process occurs at about 150 to 250 degrees centigrade for a certain time that ranges from 30 minutes all the way to 24 hours. And all of this happens in the presence of surfactants or plasticizer. And the swelling process of crumb rubber and bitumen is actually shown in this slide. So you can see here how the rubber particle absorbs the light fractions of bitumen and starts swelling. And in stage 2, you can see the formation of a gel. So as a result, an independent rubber bitumen matrix is formed in the binder. And numerous studies and experience of RBB application show that modified binders have higher performance properties in comparison with traditional bitumen. The RBB that we get has higher heat and crack resistance that bitumen that is obtained from the same raw material, but without the addition of rubber crumb. Next slide, please. This here we have the properties of the binders when modified by rubber crumb to further demonstrate the point. So data on the properties of binders obtained by combining rubber crumb, 20% of it, with oil tar. The process that was performed at a temperature of 220 to 230 degrees centigrade for 4 hours of treatment. And this is what you can see in this table. I guess we can go next slide. So the following advantages of asphalt made from bitumen with rubber crumb can be pointed out. It reduces noise pollution from the road by about half, or actually 70%. And this makes it possible to construct roads much closer to residential areas without compromising the environment much. The service life of that road is increased by 5 to 10 years. And this is achieved because cracks form on the road less often, and this saves money on road repairs, obviously. The road surface is more resistant to deformation. Bitumen modified with crumb rubber adds elasticity to the road surface, and this results in a reduction of rotting of about 75%. Such modification improves the grip of wheels with asphalt. So on such roads, the number of vehicle accidents is reduced by as much as 50% because there is not much chance of skidding. That is reduced. And it also improves the grip properties in wet, rainy weather. Another advantage is that the road surface retains its properties at high temperature fluctuation. So when the temperature rises, the traditional normal regular asphalt concrete pavement starts melting at about 47 degrees. However, a layer with the addition of polymers, or resins rather, retains its shape at ambient temperatures up to plus 70 C. And at low temperatures, rubberized asphalt cracks a lot less. And such roads can be built in any climate, basically. With the addition of crumb rubber, the mass of asphalt decreases because part of that volume, up to 10% actually, is replaced by much lighter crumb rubber. The light reflecting properties of the road are reduced, and this, of course, improves driving comfort and safety. I'm sure many of you have been driving with the sun on your face, and you'd see this sharp glare in your eyes from the road. So this is also something that we can improve. Improving this system also improves the draining properties of the pavement and prevents damage to the roads during rains. And also the service life of tires is increased because of the slower wear of the tire thread. Next slide, please. Right, so the next method of modification we'll look at is the sulfur modification. Sulfur modification is one of the more conventional solutions. The addition of sulfur does increase strength, heat resistance, crack resistance, adhesion, and also chemical resistance of road bitumen. The temperature of sulfur introduction, its content and mixing time have a significant effect on the properties of the resultant modified bitumen. So when developing a technology for the use of sulfur in road construction, it's really important to minimize the release of hydrogen sulfide and sulfur oxide during the preparation and use of these mixes. And also we need to consider the increased corrosion of equipment. It was found that when sulfur is heated to 180 or 220 degrees centigrade, there is an emission of harmful gases, toxic gases. But if the temperature stays within 120 to 145 C, and with a sulfur content in this mix of below 20%, there is not much danger of such gas release exceeding the normal health standards. There's also the increased corrosion of equipment. As I mentioned, sulfur is corrosive, so you can expect more wear on the machinery. And with the addition of elemental sulfur, its content in asphaltenes noticeably increases. The influence of all three factors noticeable. The amount of added sulfur, the duration of agitation and stirring, and heat treatment. Moreover, physical activation and stirring and heat treatment are somewhat interchangeable to a degree. So the sulfur content in the binder can actually reach 60 to 70% of by mass. But the optimal conditions for modifying bitumen with sulfur are as follows. The process temperature should be within 120, 140 degrees C. Mixing time should be approximately 10 to 20 minutes. That depends obviously on the amount of sulfur that we introduce. And the amount of sulfur being introduced is usually 5 to 7% of this by mass. The modification significantly improves such parameters and extensibility, as much as 22% increase at 25 C and 40% increase at 0 degrees centigrade. It improves elasticity by 20% and also improves adhesion to minerals. It's essential that the introduction of sulfur up to 7% by mass reduces the brittleness temperature of bitumen by 2 degrees centigrade, which affects the durability of the road surface. With a decrease in the brittle point of bitumen by 2%, by 2 degrees, excuse me, the time of intense cracking is before actually cracking occurs much. It's extended by 2.5 years. In addition, a decrease in viscosity is observed. Such as 20 against 24 millimeters square per second in the original bitumen. And with a further increase in the sulfur content, the viscosity begins to increase again. But the effect of reducing the viscosity is very significant since it allows to reduce energy consumption in the preparation of asphalt concrete by reducing the heating temperature of bitumen in the process. With the introduction, of more than 7% of sulfur, the quality parameters of bitumen are somewhat reduced, but they still remain at a higher level compared to those of straight bitumen. Apparently, with the introduction of sulfur more than 7%, part of that sulfur dissolves in bitumen, plasticizing it, and part of it remains in the solid crystalline state, providing a certain structuring effect. However, there are also negative sides to this modification method. First off, ready-made road bitumen is shipped to the customer at a temperature of 160 degrees centigrade. Modification of bitumen with sulfur at this temperature causes the formation of hydrogen sulfide and sulfur oxide. So in view of that, we need to pre-cool that finished bitumen to 120 degrees C before we can begin modification, which is an inconvenience of sorts. Next slide, please. Next thing we want to address is adhesion, and what happens with adhesion and how these problems can be solved. So the quality of road surfaces, the durability of these surfaces largely depend on the strength of adhesion of bituminous binders with mineral materials. A consequence of no adhesion or no strong adhesion of bitumen to the surface of the minerals is insufficient water and frost resistance, and that leads to erosion, peeling, chipping, and cracking, which of course we don't want. Adhesion is the interfacial interaction between contacting surfaces of different nature. Adhesion provides a connection of a certain strength between two bodies, two surfaces. Silicates that are used in road construction generally adhere poorly to bitumen, especially in the presence of water. And this is because the surface of sand and gravel particles has a pronounced hydrophilicity, as a result of which bitumen is absorbed only due to microporosity and on defects on the surfaces. So water penetrating through the pores in the asphalt concrete to the bitumen mineral material interface gradually displaces the bitumen film and destroys that road surface. So chemical modification of bitumen with adhesive additives allows to a large degree to solve the problem of adhesion of bitumen to mineral material. Surfactant molecules concentrate at the bitumen stone material interface, and they act as a bridge or glue between the bitumen and the stone material surface, resisting this displacing action of water. Various surfactants can be used in road construction. They can be anionic, cationic, or non-ionic. The most effective adhesive additives are cationic surfactants based on nitrogen-containing chemicals such as imidazolines, amidoamines, and amines. So by reducing the tension at the bitumen mineral interface, such additives contribute to better envelopment of the grains of stone material with that binder. This increases the strength and water resistance of the asphalt mix as a whole, and as a result, it extends the service life of the road surface. With the use of surfactants, the season of road construction work is extended significantly because it's now possible to work during precipitation, in rain, and in low temperatures. Some of the commonly used adhesion additives are Bitumen from USA, F4 from Germany, there's Dynaram and Polyram from France, EC06 from Holland, and quite a few others. So these additives are introduced into bitumen usually in the amount from 0.05 to 0.5%. Next slide, please. Right. So now that we've talked how good that bitumen is when modified with polymer, let's talk about how to get it. There are methods for the preparation of polymer modified bitumen. And these methods, as a rule, require an increased process temperature, something in the range of 150 to 200 degrees, and also intensive mixing of the ingredients. PMB can be manufactured or produced in one of the following ways: by introducing a solid polymer into the molten bitumen, introducing of the polymer in the form of latex into the bitumen, introducing of polymer in the form of latex into a bitumen emulsion with water, and introduction of polymer solution into bitumen melt, and introduction of a curing agent to the bitumen in addition to the polymer, and also a combination of bitumen and polymers that contain functional groups. One of the most common is the first method, that is solid polymer introduced into molten bitumen. The polymer is introduced into bitumen in the form of a powder, which in some cases, to prevent sintering, is applied to a mineral filler first. So stirring and agitation, as a rule, is performed under strong mechanical stress at a high temperature, something like 160 to 180 degrees centigrade, and sometimes actually above 200 degrees, and it takes quite a bit of time. The decomposition temperature of most polymers that are used for modifying bitumen, I'm talking about polyethylene, polypropylene, ethylene propylene, rubbers, etc., significantly exceeds the temperature of their combination with bitumen. Consequently, the reactions of thermal and mechanical destruction of polymers in the bitumen do not occur, and if they do, they proceed to a very insignificant extent. A bitumen softens when heated, and thermoplastic polymers, regardless of whether they're crystalline or amorphous, become viscous. The increased temperature accelerates the swelling or dissolution of the polymer in the bitumen. And in the production of modified bitumen, two processes are generally distinguished and used. There's the continuous production process and the batch production process. In continuous production, hot bitumen and polymer, be it in powder or crumb form, are fed into a low fineness premixer with precise control of the flow. At this stage, the bitumen is moistened with polymers, wetted with polymers, I guess. And after this pre-mixing stage, the bitumen polymer mixture passes through a mill with a high degree of fine grinding to achieve the desired mixing quality. And then that mixture is sent to special tanks that are equipped with agitation or mixing system to prevent phase separation, where the so-called maturation occurs. This maturation time depends on the type of bitumen, type of the polymers, the settings of the fine grinding mill, flow rate, and the temperature of bitumen. In the production of modified bitumen in batches, one or more mixers are used, usually two, into which bitumen and polymers are loaded in certain quantities. And then they're pre-mixed and sent to the fine grinding mill, through which they pass the required number of times. A laboratory test is required to determine the number of passes necessary through the mill, and when that number has been reached, the mixture is considered ready for use and then can be unloaded and shipped to an asphalt plant, to a storage tank, or to a tar sprayer. Next slide, please. Let's talk about one of the machines that is used for production of bitumen modification continuously. And we will speak about the machine that we know best. And we know it best because we make it. It's the USB 3, Globcore USB 3 machine for the continuous bitumen modification. At this time, this model is represented by two, the product range, I'm sorry, is represented by two models. The capacities of these models are 6 and 12 cubic meters per hour. And it can add a polymer in the range from 1 to 6% by mass, plasticizer up to 10%, and adhesive additive up to 1%. And all of that depends on the product formula. But there are already promising developments here underway to expand that model range with machines that have capacities 20 and 40 cubic meter per hour production capacity. The design of these plants that we make allows for the use of any modifier that is known today, including crumb rubber, including the various special additives, along with all known SBS polymers, which can be supplied in the form of granules, powder, or liquid, whichever is best for the operation. The plant allows for new formulations of modified bitumen in which the introduction of adhesive additives and plasticizer may be required. So next, we're going to look at the design of that machine in a bit more detail. Next slide, please. So the unit is installed, the components of the unit are installed inside a frame. The dimensions of that frame allow transporting this machinery in a standard 20-foot container. And the frame structure itself is quite strong physically, so the plant can be quickly deployed or dismantled if necessary in the field when the location of the asphalt plant must be changed. The bitumen modification process begins with loading polymer into a hopper. or a bin, as you might call it. This is done by the operator manually or using a lifting device of sorts, like a hoist. And after that, the operator sets the percentage of additives of the bitumen on the control panel and starts the plant, and then the plant operates automatically. A bitumen is heated at the time at 260 to 190 degrees centigrade, and that hot bitumen is fed into an intermediate tank along with the polymer that is supplied by a conveyor. And if the formula requires a plasticizer and an adhesive additive, they're also dosed into the bitumen, but before it's fed into the intermediate tank. Now, inside that tank, there is a high-speed turbine mixer. It premixes polymer and bitumen, and the resulting mix is fed to a colloidal mill with special profile cutters, which grind, cut, and homogenize the polymer containing bitumen, after which the finished product from the outlet of the plant is unloaded into a storage and transportation container. And that's only one pass through the mill is enough for the production of modified bitumen. And at the same time, the quality of the binder product produced in our continuous plants is not at all inferior to the quality of the materials that are produced in batch plants. Moreover, the USB plant is more reliable and easier to maintain because of all the automation of the process. And as a result, the cost of bitumen production has also decreased. Operating this plant allows the operator to set up the production of high quality modified bitumen for large volumes of asphalt concrete mix. And roads built with such mixtures in general last 2 to 3 times longer than roads that are built with ordinary straight bitumen. Next slide, please. So a little closer look at the design of this plant. As I mentioned, all of the components of the plant are installed on a single metal frame. There are 2 bitumen pumps, M1 and M2. There is the mill M3, a mixer M4. There is the polymer hopper with an auger conveyor M5. There is the plasticizer input unit M6, adhesive additive unit M7, a system of heated bitumen pipelines with control valves, VT1, VT2, VT3, and then V1 and V2. Next slide, please. So here we can take a look at the process diagram of the plant. What happens during the process is the M1 bitumen pump takes bitumen that is already heated to the operating temperature of 180 degrees centigrade. This bitumen is taken from the bitumen boiler and fed into that system. The pump is controlled by a frequency converter, so you can control the amount of bitumen input. And depending on the position of the VT1 valve, that's a 3-way valve, the bitumen can be directed either back to the bitumen boiler or to the mixer. And before the M2 pump, the bitumen is mixed with the polymer using the M4 turbine mixer. The operator inputs polymers from bags, like big bags, into the polymer hopper. And then from that hopper, it's fed by an auger conveyor driven by the M5 drive. And depending on the required concentration of polymer and bitumen, the operator can control the speed of the drive and control the auger M5, and thus provide the specified supply of polymer. There is a switch for that on the control cabinet panel. The M6 pump supplies the required amount of plasticizer to the bitumen, and that happens before the mixer. And the operator can also control the rotation speed of the M6 drive and provide a specific input rate of plasticizer. The M7 pump does the same for adhesive additive, so also controllable through the frequency converter. So in the mixing tank, the polymer, plasticizer, and adhesive additives are distributed evenly in the bitumen that is supplied by the M1 pump. So in the mixing tank during the operation of the plant, the bitumen level is constantly held between the low and high level sensors, and they are LLS1 and HLS1. And this is done by automatically controlling the M2 pump by the frequency converter, depending on the signals received from these 2 sensors. The M2 pump pumps out the polymer bitumen mixture from the M4 mixer, and polymer is then evenly distributed in the bitumen, ground, and finally homogenized by the M3 mill. And from the M3 mill through the VT3 3-way valve, bitumen enters the modified bitumen line out to a product collection tank. So through the VT2 valve, the modified bitumen can be fed by the M2 pump to repeat the mixing cycle in the mill. after which the bitumen passes through the VT3 three-way valve once again on the way out. And also through the VT2 valve, the bitumen can be returned back into the bitumen storage boiler after passing the mill by the M2 pump. So we can then go with that bitumen through the entire mixing cycle again with the addition of the necessary additives. Next slide, please. And this is a bit of a bigger picture. You can see a section limited by a dashed line. That's the USB 3 plant as a part of a larger facility for bitumen modification. So bitumen in this process is heated in a bitumen boiler outside the machine to an operating temperature of 190 to 200 degrees centigrade. And it's stirred by circulation. There is a separate pump, M1.1. That pump provides circulation inside the boiler. And after reaching a uniform temperature throughout that boiler, that bitumen is fed to the plant using a heated and insulated feed pipeline. The plant itself is heated to a temperature of 90 degrees centigrade by circulating heating oil that is provided by the pump M1.3. Once again, the hopper is filled with polymer, and the operator selects one of the operating modes for automatic operation, presses the start button, and the automatic mode commences. And the plant performs the specified program sequence. The components farthest from the bitumen input are engaged first. And then when the stop button is pressed, the machine stops itself and turns off all the components in the reverse order. And at the end of the operation, the plant must be flushed with a straight bitumen for easy subsequent startup. Next slide, please. Here, briefly, this shows the overall dimensions of the plant and the connections. So that's something that can help prepare for placing the machine on site and to prepare the correct supply and output lines for it. Next slide, please. Right, so we have modes here of operation. There are the following modes. There's modification, modification plus additives, flushing, finishing mode, circulation mode, and manual mode. So first off, let's talk about modification and modification plus additives modes. These are the main operating modes of the modified bitumen production plant. Using the mode button, the operator selects one of the modification modes. And if the operator presses the start button, the message activated appears on the top line of the screen of the controller, and the process of bitumen production begins immediately. So pneumatic valve VT1 switches from bitumen supply to the return line, switches it to the mixer, and the bitumen pump M1 switched on. And so the mixer tank is first filled with straight bitumen. And when that bitumen reaches the lower level sensor in the tank, LLS1, the M4 impeller mixer switched on. The screw conveyor motor M5 is switched on to supply polymer. And the mill, the M3 mill drive switched on as well. And when that mill, first that mill needs to spool up. So when it spools up, the M2 pump starts. And after passing through the mill and the VT3 valve, the polymer modified bitumen then enters the maturation tank, basically the tank for storing the finished product. Next slide, please. So that was the basic modification, but there's also the modification plus additives mode. And in that mode, the drives for the supply of the plasticizer and the adhesive additive, those are M6 and M7 respectively, are also started and switched on. So through the viewing window, there's a side glass that allows the operator to observe the frequency of the auger conveyor for the polymer, and if necessary, to adjust the amount of that polymer supplied. And that also goes for plasticizer and adhesive additive. And this is done by changing the frequency of the converters. And when the high-level sensor, HLS1, in the mixer is reached, the M2 pump converter increases the frequency to 60 Hertz. And if the bitumen level in the mixer decreases, then after 30 seconds, the converter of the M2 will then decrease its frequency back to 50 Hertz. So when the level increases and reaches HLS1 again, the frequency rises. So the bitumen level in that mixer is maintained automatically between HLS1 and LLS1 sensors. If the stop button is pressed during operation, the unit enters the finishing mode. A blinking finish message will appear on the controller screen. And what that entails is the M1 pump stops, the VT1 three-way valve switches to the position of supply and bitumen to the return line, the M5 screw conveyor turns off, but the M3, the mill, the mixer M4, and the pump M2 still continue to run. When the LLS1 sensor turns off, so when bitumen level drops below the low level sensor, the M4 mixer stops. Then after a certain time, when the mill current drops below a specific set point, the M2 pump and the M3 mill also stop. The active and the finish messages disappear because the process is now complete. So the condition for the successful startup of the plant is that the temperature of the thermal oil in the unit, remember the heating of the machine, is not lower than 160 degrees. Otherwise, there is a warning message and the plant doesn't start. Also, if the low level sensor in the mixer is active, that plant cannot be started as well. Next is the finishing mode. Thank you. This mode is used if the plant was stopped for any reason during the process, and it's necessary to remove and pump out that remaining bitumen from the mixer. So after selecting the finishing mode, using, as I mentioned before, if the low-level mixer is detecting bitumen, then the plant cannot be started, so we go into the finishing mode to do that. So after selecting the finishing mode with a mode button and pressing the start button, here's what happens. If that low-level sensor, LS1, is on, detecting bitumen, the M4 mixer and the M3 mill are switched on. And after the mill spools up, the M2 pump starts, and bitumen is taken from the mixer in the same way as in the modification process. And after M2 and M3 stop, the active message disappears from the screen, and the finished process is complete. And PMB in this mode is output to the product storage container. This mode is, excuse me, next slide, please, first of all. Thank you. So this is the flushing mode, and this is used when it's necessary to rinse or flush the plant with straight bitumen, or when we need to preheat it before starting or after completing operation on the unit before shutting it down. In this mode, we can start the unit with a temperature of 140 degrees centigrade. And after selecting the flushing mode with a mode button and pressing the start button on the controller, here's what happens. So the M1 pump turns on and the VT1 valve moves to the position of bitumen supply to the mixer. And when bitumen reaches the lower level sensor, the LS1, the mixer M4 is switched on. The pneumatic valve VT3 switches to the position of supply and bitumen to the return line. The mill M3 switched on, and after flushing the bitumen, that bitumen goes back to the storage tank. Then the M2 pump starts after mill spool up, and all components run like this for 60 seconds, still maintaining the bitumen level in the mixer. And then the bitumen supply pump M1 stops. The VT1 valve goes to the position to supply bitumen to the return line. And then bitumen is taken from the mixer. And when the low-level sensor, the LLS1, is off, the VT3 pneumatic valve switches to supply bitumen to the outlet. And the M4 mixer stops, and the bitumen from the mixer starts flushing that pipe to the finished product storage container. And after a certain time, when the mill current falls below that set point, the M2 pump and the M3 mill also disengaged. And after stopping of the mill, the VT1 valve switches to the position of feeding bitumen to the mixer. The M1 pump is turned on in reverse, and the remaining bitumen is pumped out of the pipes for 20 seconds. And this now concludes that process, and the plant can be turned off or a new operating mode selected. Next slide, please. This is the circulation mode, and it's used when it's necessary to run the polymer modified bitumen from the finished product tank once again through the mill. Selecting the circulation mode using the mode button, you can press the start button, and what happens is pneumatic valve VT2 switches to the repeat cycle position. The pneumatic valve VT3 switches to the position of supply and bitumen to the return line, and then the bitumen supply pump M2 starts, and then PMB is pumped into that buffer tank. And after pumping out the PMB, we can then start a modification or modification plus additives mode. Next slide, please. Now, manual mode is of course available, but it's only used really for testing individual components of the plant. It's also used during setup and commissioning, startup of the plant, and if we maybe need to return the plant to its normal state after a failure, or if there is an emergency stop, for instance. So emergency stops, when any alarm occurs, the machine stops, the alarm, there is an alarm off button, it lights up. There is a light and sound alarm that is turned on. A corresponding message appears on the controller screen. And the operator can just briefly press the alarm off button to turn off the siren. If the cause of the problem has not been eliminated, the alarm message, default message, still remains on screen. If several problems occur at the same time, these messages are cycled on the screen. So after eliminating or repairing whatever caused that alarm and pressing the alarm off button, the operation can be continued. There are two classes or types or groups, I guess, of alarms. There are critical alarms. Such alarms indicate problems that are dangerous to personnel or can actually cause destruction of the plant and its components. And there are non-critical alarms. In the event of such alarms, the plant just goes into finishing mode or just stops the cycle. So the controller display shows information messages regarding any reasons for the stop and why the plant cannot be currently started. All right, next slide, please. Right, so this here is the heart of the machine. It's the high-speed colloid mill that makes it all possible. The pumping equipment of the plant has frequency converters, so it allows to supply pre-mixed bitumen and polymer to the mill at a certain rate and pressure. So what it does is relieves the mill from the function of creating suction and discharge. And all that power that goes into the mill goes directly into homogenizing the product. The cutters of the mill have a special profile. That profile allows very fine grinding, cutting, and homogenizing of polymer-containing bitumen to produce a finished product of excellent quality in just one pass. The design of the mill also allows to change the gap between the cutters if necessary. That usually depends on the required task at hand. Next slide, please. Right, so let's talk about how good the USB 3 is, about its advantages, right? So the ability to use any known modifier today, including crumb rubber and various special additives such as SBS, any known SBS. The polymer can be supplied in the form of granules, powders, or liquid if necessary, so that is a big plus. It's capable of producing any number of products with different concentrations of additives because those are all adjustable quite easily. The product quality, excuse me, is quite good with a little time investment. The plant is very easy to operate and maintain. It's small. It means it's easy to transport in a standard 20-foot container because sometimes these plants have to be mobile to move from site to site. The frame of the machine, the frame is pretty strong and it allows for quick assembly and disassembly, quick deployment and redeployment. And that may be important when changing the location of the asphalt plant. The intermediate tank is designed for preliminary mixing of the polymer with bitumen, and it increases the contact time of exposure time, I guess, of bitumen and polymer, which takes some of the load off the mill. And the tank is equipped with the high-speed agitator, the turbine mixer that I mentioned, which allows mixing the bitumen and polymer quite evenly. And it's safe to say that the modification process is pretty much finished in that turbine mixer, but the mill just adds better stability and homogenization of that product. So there are also level sensors installed in that tank, and they help maintain a constant level of bitumen for optimal mixing automatically without operator intervention. The plant's equipped with electropneumatic valves. The compressed air can be supplied from the compressor that comes from the plant, all right? So, but it's optional if there is a compressed air source on site. the plant can be used without an inbuilt integrated compressor. So at any rate, with the optional compressor, the plant can be independent from any external source of compressed air. All of the pipelines, pumps, the mill itself, the tank with the turbine mixer, they're all heated with oil. And heating with oil is the most gentle and efficient method for heating components and bitumen pipelines. In the control system, is housed in a control cabinet, and the cabinet contains all the switching equipment, the motor protection circuits, the breakers, the frequency converters, the soft starters for mill drives and the pumps, a controller, and measuring transducers. And these controller and transducers are made by leading producers such as Emerson, Siemens, ABB, Autonix, and what have you. So the quality of components is actually quite impressive. So controls are placed on the front panel. There are push buttons. You can have start, stop, mode, alarm reset, emergency stop buttons. There are also buttons for manual control of components. There is a controller panel for PLC and pressure and temperature controllers, which also provide the readouts of these parameters. An important feature of the plant is the complete automation of all processes for the production of modified bitumen. To simplify the control, what we do is we add a pneumatic diagram to the control cabinet. It's a simplified process diagram with signal lights that allow the operator to quickly see what's going on inside the plant. The plant itself is run by and monitored by software algorithm embedded in the PLC, and this allows you to quickly customize the process settings. And it actually can be configured via the internet remotely, and it's very reliable, this PLC, and it does significantly speed up the setup of the equipment and commissioning and startup and whatnot. So some of the optional ideas that can be implemented here in this plant are sulfur supply module, polyphosphoric acid, supply module, Telfer device with scales for inputting of the polymer using big bags. As I mentioned, the compressor is optional for the control valves. The mill can also be equipped with a mechanical seal if the customer so prefers. And this is pretty much it for the USB 3. Let's go to the next slide. Now, Globe Core here, we know that the big facilities are big, right? And they also involve big volumes of products and materials. So it's not always desirable. So we got a laboratory unit for bitumen modification. And what it does, it allows you to experimentally determine the optimal formula, or maybe it's necessary to change the product on your large facility, a large production site. And this unit you can use to work out that formula. It is designed for the preparation of modified bitumen samples in small volumes, something like 12 to 20 liters per cycle. And this unit is much smaller than a full-size industrial machine, obviously, and it consumes a lot less power. The transfer dimensions are just over a meter long, 800 millimeter wide, and just over 1.5 meters high. And the power consumption of this unit is actually below 5 kilowatt. So what we do here is we mix the ingredients simultaneously dispersing bitumen and polymer using a mill. And the design of this unit also provides for adding liquid components into the modified bitumens. So on this slide here, you can see the components are also installed on a welded frame. The loading of bitumen and modifying additives into the reactor 3 is done through a hatch in position 4. If necessary, we can also add liquid components to that same hatch. So maintaining the operating temperature range of heated bitumen is ensured by heating the mixing tank and pipelines with heating cables and heating cord, really. The maintenance of bitumen in the operating temperature range, which is from 160 degrees to 180 degrees, occurs with a constant stirring using the mechanism in position 5, and it's also controlled automatically. The temperatures of bitumen and the surfaces of the components are monitored using temperature sensors, And these are displayed in the control cabinet in position 8. The components are driven by electric motors through elastic couplings. The uniformity of the process of dispersion of the polymer in bitumen is ensured by constant mixing of bitumen during its circulation through that mill in position 2. So a circulating flow of bitumen is created in the pipeline system. You can see it under position 7. And the finished product is pumped out by the bitumen pump 6. So now we see the flow diagram here on the right part of the slide. Let's check out the operation of the machine. So first, we must check the position of valve V and the bottom valve V, and those must be completely closed. Then we start the heating, and the control system can hold temperature within specified limits, mostly like 160 to 180 degrees. And when the temperature in the mixing tank exceeds 160 C, then we can load the reactor in position R with hot bitumen at 180 degrees centigrade. And this is accompanied by a green signal light on the control cabinet. That means that the mixer can be now started. And then we just press the green mixer button in the control cabinet, and the mixer starts. And then we add a predetermined quality of modifier, adhesive additive, and plasticizer to the reactor. The introduction of modifying additives requires that bitumen is at the operating temperature correctly, and that is selected during, this is selected according to the polymer specifications. So after sufficient time has elapsed for pre-mixing of the additives and the bitumen, then we open that bottom valve that has a rotating handle, and it's under the mixing vessel, and we turn on the mill by pressing the green mill button on the control cabinet. And if the mill temperature is within the required limits, the mill then starts, and the bitumen mixture begins to circulate, goes back into the container after the mill. And if the mill does not turn on and the green light next to the mill inscription label is off, that means that the pipeline with the mill has not yet reached the required temperature, and some time is required for that. So for about 1 hour, the bitumen matures in the reactor with the stirrer and the mill still on. And after that, the operator places a container for the sample under the drain outlet. The operator can open the valve V and turn on the bitumen pump. And the bitumen pump will, the bitumen then will flow from that outlet. But it's recommended to, the first bitumen that comes out for 2-3 seconds is not a very good sample, so it can be disposed of. And then you can collect the actual sample in the sampling container and take it to a laboratory for, for analysis. So after draining the prepared bitumen from that tank, we should remove the bitumen from the mill, the outlet inside the tank, and from all the pipelines. And to do so, the operator just closes the bottom valve without turning off the bitumen pump. And in this case, all the remaining bitumen is pumped from the mill and from the pipelines. And after a complete draining of the bitumen from the system, the operator just turns off the pump, pressing the red bitumen pump button, and closes the valve V. Such a lab unit is especially important if the large facility plans to sell the product to the outside customer, and a change in product formula is coming. So product quality is important. So it's better to run a test on the smaller machine than use tons of material in the bigger facility with unknown results. And so this brings us to the end of our presentation. I do hope that you've learned something useful and practical from it. It took a lot of effort to prepare all this information, and I would like to thank my colleagues here that were answering your questions in the text today. Thank you very much. So, and this thank you goes out for you. Thank you for being here. One thing before we leave, there's going to be another at least a webinar on the topic of bitumen, probably dealing with bitumen emulsions. And this is going to be in September. So please stay tuned if you're into this topic. We're going to talk more on that. And with that, once again, thank you very much for being here. I hope you enjoyed this as much as I enjoyed giving the presentation. And I hope to see you back at Globe Cortex School in the future. Thank you and goodbye.